But okay. Hi everyone. Welcome to a theory seminar during our week or reading week. One thing I think Janani recently stepped down as one of the organizers of seminar, so let's thank her again. So for near future, it will be me and Helia. If anyone wants to volunteer, there's enough work to do. Okay. All right, without further ado, John is going to talk about her work with Gary on me. Go ahead.
So I was the organizer for one semester, and I think Helia's already done it for longer than I have. So we should. And also, this is my last seminar talk. I don't think, hopefully, if I graduate, I don't think you will have to put up with listening to me for much longer. Okay, so let's see how this goes. We're going to be talking about single source shortest paths in semi-streaming. Yes, okay, let me start by defining a model. I have done this many times before. Here, at least, you have a graph with n vertices and m edges. And the vertex set is already given to you, and the edges are not known initially. And the edges are going to come one by one in some arbitrary order that you don't have any control over. And you'll see all the m edges. And the catch is you can't really store all the edges to process them. You only have limited order of n polylog in space, and you want to process the graph using whatever you can store in this limited space. So this pass over the edges, or once when you see the edges, I'm just going to call this one pass. And this stream of edges can be repeated for multiple passes if you wanted to. Okay, we're working with this model. Any questions about the model? I don't think so. All right. Okay, so the aim is to just find shortest paths. So you're given vertices S and T at the beginning of the stream before you know any edges. So you already have the vertex set and you're given two specific vertices S and T. And you want to output a path between S and T at the end of the stream after, yes. Yeah, so initially when people started doing this, they were trying to get things in polylog space as opposed to n polylog n space. Okay, so that was classic streaming, as in you want something logarithmic in the number of vertices also. But this is semi, as in you're allowing some dependence like n times polylog, as in, so it's not completely as low space as possible. Anything else?
And also in this problem, you given that you want to output the path itself, you need n space in more space.
Yes. You want to store it at the end. So I mean, you can actually just ask for distance. And that is still hard, but we will see. Okay? So I'm asking for the path at the end of the stream.
So even for distance, you can't do
We'll
it.
talk about it. So what can you do here? Let's start with very simple algorithms. What do we know classically to find shortest paths? We can run BFS. So what is going to happen if you try to run BFS here? You have this source vertex because this is already given to you. And in one pass, my claim is you can only grow one level of this tree. Okay. So why? Because you know that these are neighbors of S, but you don't have any control over the edges, so you don't know neighbors of these vertices to continue this tree forward. Okay, what if these things appear at the end of the stream or something like that? So you don't know what's going on. But you can just grow this one more level in another pass, and so on. So finally, in 3 passes, you'll figure out the shortest path tree of this graph. Yes.
Grow a forest.
Sorry?
Did you grow a forest?
A forest or something we basically want.
Because you have n space here.
Yes, you can grow a forest, but what source would you start with? They still don't know. What would the aim be? Sure, you have enough space to grow a forest.
As
Yes.
the shortest doesn't make sense.
Yeah. So this naive algorithm is going to use linear number of passes and run an O tilde of n space and actually output the BFS tree. Okay. I am going to let's just look at one pass. So in one pass, we said we can grow one level of BFS tree. Can you do anything better and actually get some kind of approximation or not? We will see. And so this is something that we have completely answered, like what you can do in one pass. So we know that we can get log n over log n approximate shortest paths. Okay, and this is also the best you can do. And this was known like 20 years ago now. We will briefly talk about how you can do this much later during this talk. But for now, I just want to just keep this ratio somehow. You can actually do something in one pass, which is not trivial. Okay. So yes, the obvious next question, if this is the best you can do in one pass over the edges, I am going to tell you many, many times these are the edges and multiple passes over them. Can you do better and get a better approximation ratio or not? So yes, you can actually get arbitrary 1 plus epsilon approximations for any epsilon value that you want. And we're interested in the number of passes it takes for you to get this approximation. So this has actually slowly been improved over a lot of results. I am only going to give you the state of art. So for getting a 1 plus epsilon approximation, we're trying to focus on the number of passes you need to do this. Okay. So before this work, we knew that you can actually do it in polylog over epsilon square passes. This is from Becker et al. This log is just like some large unspecified constant. They don't explicitly keep track of it. The epsilon dependence was more important for them. And this was improved to polylog over epsilon number of, sorry.
Does the C itself is not epsilon or that?
No, the C is just some large constant.
So the only the epsilon.
Epsilon square is coming in, yes. Okay, so this is again some large polylog over epsilon. Okay, so the epsilon dependence is better. You can get polylog over epsilon number of passes. So it's just some large constant C. And in terms of lower bounds, again, we're going to focus on getting a 1 plus epsilon approximate, but we'll see that later. So this paper, Feigenbaum et al., it said that if you want to output the set of vertices, we're not talking about approximation anymore. It's just saying you have a source. I'm asking for a set of vertices at a distance at most k from this source. Okay. So that needs omega of k passes, but it's not true for every k. It is only true for this particular range of k. Order log n over log n. Okay. And this was later improved by Guruswamy Onag. And they said that even if you just want to find two vertices, whether they're at a distance of at most k or at least k plus 1, this is going to need omega of k passes also for, again, k to be order log n over log n. Okay. So these lower bounds are for the hardest version of the problem for exact shortest paths. Okay. And essentially the message here is we saw that naive BFS tree algorithm is growing slowly, like one level in one pass kind of thing. That seems to be the best you can do for these very short distances of like log n over log n kind of thing, for finding exact shortest paths and exact distances. So we're again focusing on a 1 plus epsilon approximation. We can just extend these bounds. If you just compare k plus 1 versus k, you'll get some kind of lower bounds for specific values of epsilon. But those are the only lower bounds we can get for 1 plus epsilon approximation. So you'll have like omega of 1 over epsilon kind of lower bounds for very small epsilon.
That's the passes?
Yes, the number of passes. That's what we're looking at. Yes. So let's recap again. What is the state of art? For upper bounds, these papers give you an order of 1 over epsilon times polylog n. This is the number of passes, and we're only focusing on a 1 plus epsilon approximation. Okay. And in terms of lower bound, you get little omega of 1 for some very small values of epsilon, and it's very specific. Okay. So what does our result do? We're able to get an algorithm which runs in log square n over epsilon number of passes and gets you 1 plus epsilon approximation. And we also show that if you want any constant approximation, you need log n over log n passes. Okay, so this is true for any constant. And yes, of course, there is still a gap. this gap. We cannot close this gap.
Your program also extend to the epsilon.
The dependence is like 1 over alpha times log n over log n for any alpha approximation. Okay, so like for any 20 epsilon, whatever, you still need log n, 20 approximation or something like that, you still do it. So I mean, I can put it as to get exact shortest paths, we knew that log n over log n was true up to some value. We're just extending that to any constant approximation also. And it does not give you anything better for exact shortest paths. Let me be a little bit more formal. What is the algorithm doing? You're given a source vertex S. It's actually going to give you a 1 plus epsilon approximate tree, as in single source to all the other vertices. And this is true for any epsilon greater than 0. And you'll get it in 1 over epsilon times log n over log n square number of passes. Okay, so this is the strongest version of the problem in that you're actually outputting a tree and a approximate shortest path to every other vertex in the graph. And let's look at something very small that I can ask. You have two specific vertices S and T, and I just want to estimate distance between S and T up to some alpha approximation. I don't even want the path. You just output the value of the distance. And for that, it is saying that you still need omega of log n over log n passes for constant alpha. Okay. So the gap now is a log n over log n factor. So let's look at, I'm only going to talk about the upper bound. Okay, I have some slides for the lower bound later if someone is interested. Okay. But we'll talk about that if someone wants to, only at the end after. So let's focus on the upper bound, what the result is. And it's a simple algorithm. I will hopefully give you the entire algorithm and the entire proof just during this session. Okay. So you're given a vertex S at the beginning of the stream, and you want to output a 1 plus epsilon approximate shortest path tree starting from S to all the other vertices. I will slightly relax into log square n passes. What do we want from this shortest path tree? For every other vertex U, you want the distance in this tree between the source and you to be at most 1 plus epsilon times the actual distance of the graph. Okay, this is just a definition of approximation. You'll have a tree which obeys these properties. So we want to output this at the end of the algorithm. So let's look at let's briefly talk about, I'll just say a couple of sentences about what the prior techniques did. So both the AGGST paper and the BFKL paper, they are solving this more general problem of transshipment. Okay. And you can view them as a boosting framework in that they'll have like crude, bad approximations for transshipment, and then they'll slowly make it better approximations. And good approximations of transshipment then will give you like good approximation for a shortest path also. Okay. But mainly what I want to say here is our work is not a boosting framework in this sense, where you have a bad approximation and you slowly make it better. You're actually trying to sparsify the graph and solve exact shortest path on fewer edges repeatedly. So the focus is always on which edges you're going to focus and which edges you're going to find a shortest path over and how you're sparsifying the graph in the next step and so on. Okay, so it'll become a little bit clear, but we can view this framework as you have too many edges, you don't know what to store, but then you're somehow finding relevant edges to store, focusing on them, gaining some information, finding some other relevant edges to store, gaining some information, and moving through and getting it for doing this for multiple passes. Okay. And yes, this is based on ASADI 24 for matchings. And now there are, I think, a couple more results for general LPs which do this kind of a sparsification. there are a lot of similarities to the multiplicative weight method, and we can talk about this later if someone is interested. Yes.
Is it helpful to know what transshipment is, or it's not relevant so much?
It's not relevant to the rest of the talk, but I can tell you at the end of the talk if you want to know.
So it's on way to mean close from S. Yes.
Not just like you can have general demand, yeah, you can have general demand and surplus in other vertices, in all the vertices in one. Okay, so I am going to split this. I introduced the model and we talked about semi-streaming and sparsifying. But for now, let's just try to find an algorithm and we'll worry about implementing it later. Okay, so forget about the semi-streaming model. I'll give you like an algorithm which works in any model you want. And then I'll show you how you can implement it with low space. So this is roughly the framework. I will be more specific bit by bit in this algorithm slowly. Okay. So let's start with the first step. It is just to find a baseline approximation. Okay. We're not going to be boosting this approximation. It's just something that will help you through the algorithm. And how the algorithm is going to proceed is it's going to maintain these sort of importance values over the edges. Think of it like a big table with many entries, and you're somehow storing these entries and using them and changing them through the course of the algorithm. Okay. And over many iterations, this is how you're changing the importance values. We'll have this thing called a processing rule, meaning you have some table of importance values currently. If this importance values may be reflected like a good shortest path tree, we would want to use them and extract all these edges. This is morally what the processing rule will do. And the update rule is going to do something like, okay, your importance values are not that good. You did not know what you were doing. You got yourself into a bad place. How would you change them so you can make progress later? Okay, so this is the update rule. So the importance values you can picture as a big table. And then the first one is using them to get information from the graph. And the second one is trying to figure out how you can change them to make more progress later. And maybe some edges are important, you miss them, and so on. Okay. And at the end, you'll have like some information over the course of this algorithm you've gained, and you'll find a tree based on this. Okay, so this is very vague right now. We'll be very specific for each of these things one by one. So what is my baseline approximation? So this is the part where I said we'll talk about the one-pass algorithm. We're going to talk about it now very briefly. I'm going to use something called a spanner. What is a spanner? If you have a graph, in any subgraph, the distance in the subgraph is going to be larger than what you already started out with, right? But a spanner has this property that it is a subgraph, and inside this subgraph, for any pair U and V, it's nothing to do with S, it's just any pair U and V, the distance in the spanner is going to be at most an alpha factor off from the original distance. So you have the graph, its distance originally was d of u comma v. And if you take the subgraph, the distance in the subgraph is going to be greater than u comma v. But it's also saying that it's not too large, it's only an alpha factor off. Okay? So if a subgraph has this property, I am going to call it a spanner. And as you can see, it actually is true for every pair of vertices u and v, which means it's going to approximate shortest path distances from your source also. So it approximates these distances up to some alpha factor. And it turns out you can actually store spanners with this log n approximation ratio. Okay, and the algorithm is simple also. You can do it in one pass. And this is essentially what the one pass algorithm does, and you can prove that this is tight. Okay. So what you're going to do is just look at an edge. Okay. If the edge is u comma v, see if there is a short path between these two vertices. If that happens, your edge is kind of useless. It's not adding anything to your graph, so you get rid of it. If that doesn't happen, then you keep it. So basically, you look for short cycles. And if the short cycle exists, get rid of the edge. Otherwise, you keep it. So if I specifically look for a log n spanner, means I look for cycles of length log n plus 1. we can prove that whatever graph you get at the end is going to be a good spanner with this approximation ratio of log n, and its density is also small. So you can store it, you won't store too many edges. Which one?
That's the power cycle. Or no, it is power cycle.
Keep it.
It does not create a cycle.
If it creates a cycle, then it's useless because you have another path. Okay, if it doesn't create a cycle, then you keep it.
It's not a cycle. Yeah.
Oh, does not create a cycle. I see. Okay, fair enough. Good. Okay, I'll change it. Thank you.
Before then you go to the house.
It's grammar issues. Oh, yeah,
But I have stopped compiling, so.
it's fine. Okay, so this density is also going to be small enough to store. Okay, so you can just keep this. And this is all I'm going to use for my baseline approximation. Okay, so it's a log n spanner. The Moore bound is, so these things will have small girth. The Moore bound is a way to upper bound density of graphs with small girth. This upper bound of the density comes via this one. With large girth, yes. Okay, with small girth, then it'll be very dense. Large girth, it's upper bound on density.
Basically, the smallest bunch.
Smallest cycle has large length, yes. Yes.
You can replace the login with an alpha. Get an alpha approximation. Store it. That's the issue.
Yeah, the density will be something like n to the 1 plus 1 over alpha kind of thing. So it'll be too much space and you can't store it.
But otherwise, such a greedy approach, as he asked, works for any alpha.
It works for any alpha. Yeah. Okay, so I filled out this thing. Yeah, you have a baseline approximation now. We will use it after this. So I was kind of vague about what these importance values are. So it's just saying that we're picturing it as a big list of now some numbers written for each edge. So at this point, I will just say that initially when you have the whole graph, you don't know which edges are important to start with. You don't know any information. So I will just start by assuming each edge has an importance value of 1. Okay, so before I start any processing or update rule or whatever, my table will just have a bunch of 1s and that's it.
When it's not only dependent, you can't store all of these things. So somehow you also have to.
Yeah, this is what we'll come to later at the end. Okay, like now we're picturing it as a list. Okay, I'm not telling you how you can actually store it or figure things out yet. No. Okay, so this QE values are going to be 1 for all my edges when I start with, okay, initially. So this many iterations is something we'll come to later, and how many times you'll have, this is telling you how many times you'll have to do these things repeatedly. Let's just look at what this processing rule does. Okay. So we have this big table of QEs over all the edges, and the main takeaway here is if these QE values were already very, very good to begin with, then we want to gain some information about the graph and keep it, okay, based on these QE values. I have artificially created an example for you where these shortest paths have actually somehow surprisingly QE values of 1. Just think of it as something very large. And every other edge has these very small QE values. So in such a situation, you want to actually just retain all these edges. How are we going to do this? This is something that is kind of standard in this model. You're just going to use these QE values and sample a lot of edges weighted by these QE values. Okay, so let this capital Q be the total value for like the sum of all these things. I'm just going to sample each edge independently with weighted by its QE value times some polylog n over epsilon. Okay. Essentially, what is this saying? You'll have O tilde of n over epsilon edges totally, okay, with high probability, and you're taking each edge weighted by its importance value. Okay.
And this is where you want us to be model independent, right? Because like in the streaming, we cannot keep all these values, right? QEs.
Exactly. You cannot keep the QE values explicitly. So I want you to think of it as a big table. Yes. Okay. So when some edge comes in, you'll be able to go look it up somewhere and then you'll get the QE values. And then you just sample it based on the QE value.
Then you can also not sample them independently, right? Because they're being given to you as a string, right? So this sampling is also something you deal with it later. So
you can sample them independently. This is not the problem. It may happen that if you keep sampling independently with some very small probability, you end up with too many edges and you can't store all of them, but that doesn't happen. Like that happens with 1 over poly n probability. So that you deal with. So if some edge is coming, you have some PE value, you can just figure out, just toss a coin with some, you can just keep it or not. Yeah, exactly. So this independence we can deal with. If I know this little QE and capital QE, I know what to do here. Yes.
Something good. Are you saying explicitly you have QE somewhere or you don't count that memory?
Yeah, I'm not counting it now. Just think of it as explicitly.
For now.
Yes.
It's not
Yeah.
that you're actually.
No. Okay. So this is the main step where we're trying to retain information based on these importance values. We had the baseline approximate spanner, and we got a lot of edges here. I'm calling it F. Just find a shortest path tree from your source inside H union F. Okay. And then you just keep the tree. So what will happen if your QE values were good? F is a good sample and your tree will be good. That's what I want you to remember. Okay. So we've.
sorry, it makes sense. What do you mean by good there and goods? And like there's many goods. So what do you mean by both goods here? Like, are you improving the log n spanner from?
We're not improving the log n spanner. I mean good in the sense of, let's say they were actually kind of accurate and were reflecting the importance that the tree edges would have. So let's look at this example. Exactly. So in this example, the QE values were large only for some good tree edges. And if they were good, you want to keep these edges. So this is the processing step. Okay, you sampled a bunch of edges weighted by their values, got a sample, and you somehow found a shortest path tree in H union F. Okay, so let's look at this update rule. And this situation is something I've again artificially created. You've ended up in something very bad where QEs were small for all the edges that you would hopefully want to retain. So if that happens, you want to change them so you at least have some hope of making progress later. Okay? And say, okay, this edge is kind of important. You miss this, you have to focus on this. Okay, increase its importance kind of thing. So you again have QE values over all your edges. In the processing step, you would have found a tree, okay, based on the current QE values. And now we want to perform a check. Okay, so is this actually a good tree? Are these good values or not? So this here, all these bad edges have like very large values, which is bad. We don't want this. Okay. So what we're going to do is let's just look at triangle inequality. Okay, we're dealing with unweighted graphs. If some edge u comma v was actually, kind of useless, this value would be less equal 1. Okay. So you have this tree. Inside that tree, look at what is happening to edge uv. So it's like a Bellman-Ford view of shortest paths. So let's particularly look at this edge. Okay. So if this edge was not missed, or if this edge wasn't important, what would happen? There would be a short path from this vertex to this one of some length. Okay. But now there's a path of length 3. Now, if I look at any edge u comma v, if uv was here, what is going to happen? You can always go to u through v and go to v through u and so on. So these distances would differ by at most 1. Okay. But if these distances are at least 2 and so on, adding this edge u comma v is going to help your shortest path tree. Okay. So this is how I'm checking if I've missed an edge, whether it's important or not. And for any edge that violates this situation, meaning this edge would have helped your tree become better or a better approximation, for those edges, I'm just doubling their importance. Okay. So here, this value is going to become 2 delta. So if your QE values are bad, your tree would be bad. There would be a lot of edges which would make the tree better and actually give shorter distances. So those edges, you're doubling their importance value. So this is it. This is the update rule. You're just going to
decrease the QE for.
No, I'm not doing that. No, it is just doubling. It is always increasing.
Pretty normalized percent.
Yeah, exactly. There's, I am not saying exactly with it. Okay, so you're doubling the QE values for the edges that violate this triangle inequality type statement in the tree that you got earlier. Okay, so this is my update rule. And we're almost done describing the algorithm. This is the final part. I want to repeat this for log square n over epsilon iterations. Okay. And the final thing I output is going to be just look at all my trees from this processing step. As in, you'll have log square n over epsilon trees from each of these steps that you collected. And then you look at the spanner also. And together, this will have a lot of edges. Just find a good tree from this and just send it. Okay.
So you're taking union of the spanner and the shortest path tree and taking the best of all of them?
Yes. Taking the best as in this is just a lot of edges. It will be a connected graph because I'm storing trees. And then
Sorry, is it union of all these shortest path trees, or I'm a little confused by the last statement.
So I have shortest path trees from all these iterations. And I also have a spanner. So it'll have T1, T2, and so on till Tk along with the spanner. This will be a lot of edges. Look at all these edges together.
Together. So
Yes.
in the union of all.
And then output a final tree based on everything here. Okay, so you can have some edges from one tree, something else from another tree, and so on. It's a mix of everything. Okay. So this is the algorithm. That's it. I'm not missing. Yes.
You could want to store all the Fs, right? Or is that too late?
I could have stored all the Fs. It would not have, yeah.
No, but the Fs, then you go to n log to the 4, right? Because if they have a bunch of edges, they have n log squared n. And then you're doing that over log squared iterations, right?
Yes.
It's not that. That's why you always store the trees.
Lot, but they could have helped.
Yeah,
It-
she wants the 2, right?
They want to not get right.
I did not really say which log was okay.
But it could have helped. We were talking about like wouldn't help.
It would not help, exactly. Yeah.
Yeah, that's it. So I say, C, you don't care in the memory, right?
Yeah. And also, even if I had some edge in F, you already have shortest path tree based on that. So I don't think it would have
Yeah, you
helped
don't need
either.
it.
Yeah.
Join with another.
Maybe, sure, it could have run with another F. I'm only storing the tree. It'll give you one shorter log factor. Okay, let's go with that. All right. Okay. So any questions about the algorithm? This is the entire algorithm.
Actually, I think what you said is correct. I mean, in F, any edge of F compared to T is a stretch only by 1 plus epsilon, by nothing, actually. No?
There is no stretch to begin with, I think. No, yeah.
The edge is not a stretch across all of them also, you know, this. No, I think it was factor too, so.
You won't lose, you're saying you won't lose more than like a factor.
I think it was a factor too, for now, but that's it.
Yeah.
Anyway, okay. We can let me think about this later. I'm not able to figure it out now. Okay. I am not going to tell you the implementation details. Yes, you had a question? No?
Actually, I don't know if you I think that might be wrong, but still, nothing.
All right. So before again going into the implementation details, I will just prove that this is the correct algorithm and it works. Okay, while we have this thing fresh in our minds. So this is going to have two main steps in the proof. Okay. So the first step is showing that in each iteration, the total weight of all these importance values together, it doesn't increase too much. Okay. Conceptually, this is saying your tree or whatever sample you got, the processing rule you did, would actually have been a good sample. So it's not like you would have missed too many heavyweight edges or heavy importance edges, or increase them or double them. Okay, so we'll see a little bit more explicitly, but this is essentially saying that your sample would have been good. And the next part is going to say no one edge is going to be violated, as in you won't double it too many times across all these log squaring iterations. So it's also saying if you had some edge which just kept doubling constantly and you kept ignoring it, that won't happen. It's not like some edge will just gain a lot of importance where you don't even see it, you don't pay attention. It's not going to be violated too many times. And then you'll show that the total violence across all these iterations is going to be small, and we'll give you something. Okay. So let's look at the first part, meaning we want to prove that the total weight does not increase too much. Okay. What is this saying? When are you increasing the weight? You get this tree T based on QE values from the processing. Okay, so you sample something and then you get a shortest path along with F and T. Okay? And then you double these QE values later, which means you're increasing the weight. But we want to try and show that this weight increase, the quantity is not going to be too much. So these trees are going to be moderately good, meaning they won't have many heavyweight edges which are updated. Heavy importance edges which are updated. Okay. So let's be a little bit more concrete. I am going to call, let's look at some specific tree. Okay, it doesn't matter if for a specific tree, let me just define these things first. A bad edge for a tree would be just something that violates this triangle inequality. Okay. Meaning something that you would have updated if this tree ended up as your shortest path tree. Okay, so this edge would have made your tree better. That's it. And a bad tree would be something with a lot of, like the weight of these bad edges is super large, as in it's an epsilon over log n fraction of the total weight you started out with. Okay. So you have these QE values already. A bad edge would be something where you're violating triangle inequality for a specific tree. And a bad tree would be something with a lot of bad edges, as in the total weight of these bad edges is large. Okay. So if my tree was good, as in the total weight of these bad edges was less than epsilon over 10 log n fraction of these things, then my claim is I'm okay. Okay, my total weight is not going to increase too much. Why? Because my new values are just going to be these ones plus the weight of the bad edges. I'm just doubling them. Okay? So the new values are just going to be 1 plus epsilon over 10 log n fraction. So we want to try and prove that you don't end up with a bad tree as your shortest path tree. So this is what we will show. Like a bad tree actually ending up as the shortest path tree is going to be happening with very low probability. Okay. So when will this tree actually end up as the tree at the end of the processing rule? Okay, so none of the bad edges for this tree are going to be sampled. Okay. Let's go over this slowly. If some bad edge for a tree was sampled, what would happen? This bad edge would be accounted for when you pick the shortest path tree. So you cannot end up in a tree where this edge would make it better.
Well, I guess in this case, you also don't end up with T in the end, right?
Yeah, exactly. T. You won't end up with that either. Like for a tree to be chosen, none of its bad edges would be picked in your sample. Okay. If they were picked, this is not the tree that you would end up with. You'd end up with some other tree. Okay. Which means for some specific tree, for this to end up, none of its bad edges should be sampled. Okay. And this kind of argument is going to be sufficient for us. We say that the total weight of these bad edges are large, okay, because we're trying to say that a bad tree does not end up being a shortest path tree. This is the standard inequality in computer science. If you just use that this weight is large, the probability that some bad edge is not sampled is going to be something like this. And if you just add it over like bad trees, you'll say that the probability that a bad edge is sampled is going to be something like exponential minus n log n. Okay, this is not even polynomially small, it's actually exponentially small for each specific tree, okay, which is bad. After this, I am going to use a very, very loose union bound. Okay. There are totally only 2 to the n log n trees anyway. Okay, so just take this up and you'll get that with exponentially small probability, you'll end up with a bad tree. Okay. So what is this saying? Is just saying that the total weight of all your importance values is going to go up by at most 1 plus epsilon over 10 log n factor. Okay, like multiplicative factor over each of these things that you're doing. Yes.
That makes sense of the calculations. You fix some kind of a bad tree.
Mm-hmm.
It would correspond to some edges which are the bad edges, and you're just asking for the probability that you are not sampling these.
Yes, exactly. Yes. I'm asking for the probability that this tree ends up being the shortest path tree,
Tree.
but
and
that's
that
an
is
upper
only
bound.
if
Yeah.
These edges are not sampled and such. And you get some upper bound on the probability of being sampled, because basically you're saying there are too many bad edges. Probability that you don't sample any of them is going to be really
Super
tiny.
small. Yes.
So you wouldn't really end up in it.
Mm-hmm. Okay, so you won't end up in a tree because no bad edge being sampled is going to be super small.
Yeah.
There should be like parentheses there, right? That times f is not in the denominator, right? It's the numerator.
Sorry?
In the previous line. In this, yeah, this is the numerator.
Oh,
right?
this,
This-
yes. Times f is like there's a parenthesis here.
Yeah.
All right, okay, so we've shown that the total weight goes up by at most 1 plus epsilon over 10 log n factors. The rest of this is simpler, okay, than this kind of a tree argument. We've shown this. The next part is to show that no one edge is violated too many times. So this part, we're just going to use the previous bound we had to do it. Okay. So too many times, as in my actual bound is going to be, I will show no edge is going to be doubled more than order log n times. The total number of iterations was log square n over epsilon. It's saying that inside these many iterations, the number of iterations where some edge gets updated is going to be at most order log n. So we said that the total weight of the edges goes up by 1 plus epsilon over 10 log n factors. Initially, we started out with giving importance of 1 to all my edges. So the starting weight was m. Okay. So the maximum total weight, it can only be at most this, because it's just log square n over epsilon iterations. Okay. So this is bounded by n cube for ms as well, something like that. So since weight of one edge doubles in each round, the total number of rounds that it can double is again order log n only, because otherwise you just violate this. So we're comparing total weight to one single edge weight and saying that this one edge weight cannot be the total weight. So the total number of bounds times you're doubling it is order log n. Okay?
Sorry.
Yes.
So think of that upper bound as mn instead of n cubed, or what if I'm?
You can think of it as mn. Yes, that is fine.
Yeah, if m is not m squared, then
I don't think it'll give you anything better than this log n here, though. So
no,
yeah.
mn is what would give me this, but I just wanted to. That's really simple.
Yes, it's just saying m is at most n square. So yes. All right. Okay. So no one edge is violated too many times. Now we're almost done. Okay, which is proof. There's one final step. Okay. So we want to actually say that these things will give you a shortest path at the end. Okay, the shortest path tree at the end. That is the thing that is left. Let's say there are totally r iterations. R was log square n over epsilon. Okay. Pick one tree at random. Okay. And this was the violations that we've been working with, meaning the distance between S and U and the distance between S and V. Okay? So we said that this distance, if it is violated, this is at least 1. No? My claim is in a random tree, for every edge U comma V, this distance is at most this value. Okay, so on average, the total violations for a particular edge is not going to be more than this.
Sorry, could
Yes.
you say like one sentence of why am I thinking about this step? The other ones are good for me, like I got the intuition once the same multiplicative weights, right?
Yes.
But why this one?
So we're looking at, sorry?
This is the average step of multiplicative.
Yeah, kind of, yeah.
Oh, that's okay, that's a thought, thank you.
Exactly, that's what I was going to, like you want to look at all the solutions and there some solution is good. We're looking at all of the trees and saying that for some edge across all these trees, average is good. Yeah. Okay. So we're looking at all the trees and picking one random tree, saying that the average violation is at most this. So why is this true? I'm just going to say that if some edge is not violated, if UV is not violated, then this distance is at most 1. Yeah, because this edge would not have helped, this distance would have been, okay, this edge was useless in the tree anyway. Okay. Now we had some bound on the total number of iterations where some edge was violated. Okay. So this was log n many times out of log square and over epsilon iterations. So on average, it will be at most epsilon over log n iterations that this would be violated. Okay. Now the final step, why is this log n? We had that one spanner that we were using through the algorithm. Okay. So this is the place where I am using the spanner. It's saying that even when something is violated, it is not violated too badly. Okay, the distance between like SU and SV is always going to be at most log n. So even in the trees where you're missing this edge, you added and doubled its weight. We use the spanner to get the trees out. The spanner has good edges which kind of replicate UV, okay, with some stretch factor. But this stretch factor we fixed to be log n. So even when it is violated, the violation is at most log n.
So, a little further, so log n was like the multiplicative factor for spanners, right? When, in the sense that whatever is the shortest distance, whatever you see in the spanner would be log n factor larger at most. So now I'm confused when you're taking difference between, like, if it were additive log n, this feels more immediate. I'm just very puzzled when it's multiplicative.
So I am using the multiplicative distance when it is violated. Like this is a multiplicative bound only. Okay. The one was just to say when it is not violated, it would be at most this. Think of this as
that when an edge is, when we say violated in the sense of the UV edge is not present, then this shortest distances between these two is at most, difference between the shortest distance between SU and SV is at most only log n. Is that way?
Yes. So more like, let me say it like this. This distance, you agree that it is almost, it is always going to be at most distance between UV because this is triangle inequality. Okay. So this is coming in because this distance between UV is at most log n. Okay, there is an edge. I'm looking at specific edge UV, so this distance is at most log n anyway. Okay. So this is it's saying that average edge violation across all my trees is at most 1 plus epsilon. Okay. And there's just one final step. I will look at a short path and then actually say that we get a good path later also. So this is an ST path. Let's say it has length L. Okay. So I'll just write it as a sum of distance between V1 to S, V2 to S, and so on. But there's one step I've skipped over. It's not very hard. You can write it as the sum of the violations between all these edges in the paths. Okay. And this will give at most 1 plus epsilon times L. And we have, this is the full proof. Hopefully we have proved it and I've somewhat partially convinced you at least that it works.
But you're missing the QEs, right? Because you're storing all of them.
Yes, that is the one thing that I haven't told you. We'll come to it. Yes. Any questions till now? Okay, so this is the final algorithm. We haven't talked about how to implement it yet. We will do that now. And it's saying that we're getting a 1 plus epsilon approximate shortest path tree in log square and over epsilon iterations. Okay. The tree is coming by looking at all the trees from the processing rule and the spanner together. So as Raval asked, how do you implement this? I'll just again go over this step by step. The first one was just a greedy algorithm that we saw, and we already knew how to implement it at one pass from the Feigenbaum et al. Paper. It's fine, okay? Just do one pass, figure out H, and keep it. And this one is kind of simple enough, as in if you're starting out and you're giving value of 1 to every edge, it's okay also. Like you just know that this is going to be 1. And for the other steps, we'll see how to implement each iteration in constant number of passes. Okay. The main idea is you store the trees instead of storing the QE values, which will just allow you to recompute values of the QE when you need them. Okay, so you're not explicitly keeping them anywhere. You do this sub-processing rule. Okay, so initially you're able to sample them and then you'll get a tree. Just keep this tree. For every iteration, you keep this tree. So when you look at some QE value and you want it later, you're going to look at all the trees before, see how many trees you're violating it in, and 2 to this number is going to be this QE value. So when some edge comes in, you can figure out its QE value, figure out the total importance by just one more pass over the edges, find it, and then for each edge you can do this. So in constant number of passes, you can implement this. Okay. So essentially how you're doing this, you're just pushing this step for later. Okay, you're just keeping the trees. You're not doing this now. You're just like, okay, I'll do it when I need to. And since you have all the trees on the spanner, you can output the path and you're done.
But also you just store all the QEs, right? Because like you only see like n times log c log to the cn many edges anyways, and what you can't see can hurt you, right? That's kind of the moral of your algorithm here.
No.
For all the edges, right, when you're sampling it with probability proportional to QE, so you need to compute it for every edge.
Oh, no, right, yeah, okay, good, yeah. So if you see the edge that you've never seen before, you say, okay, that's 1. I know how, you know how to compute, right? Yeah, I see.
Okay, so for
Right,
some
right,
edge,
yeah.
even if you haven't stored it, its value is
because that is
changing.
the same.
Yeah.
Right, that changes because of the tree, right.
I'm not sure I think I've seen before the value might not be 1.
No,
Yeah.
not 1, yeah. You compute over the tree, yeah, exactly. You look at the trees and then you're able to compute. Okay, good.
Okay, so we're done with this step also. I'm going to conclude now, and I think we're right on time. Yeah, this is nice. So we gave an algorithm for a 1 plus epsilon approximate shortest path tree. It runs in O tilde of n space and log square and over epsilon passes. And the framework was hopefully simple. It looks like I've got it. So you're repeatedly solving shortest path on these sparse subgraphs. The focus was on figuring out which edges to sample, and then how are you processing them to get something out, and so on. You're not really boosting the spanner approximation to make it better. Okay, so it's sparsifying the graph in a nice way, repeatedly. And it can be de-randomized, and it works for weighted graphs also. And it also works in dynamic streams, as in streams where edges can be deleted, then inserted, deleted, then inserted, and so on. Okay, there are updates. We're not going into any of this. We can talk about this offline if someone wants to. Although the weighted extension is not hard to see. Yeah. And the final result is this approximate shortest path in O tilde of n space. There's an upper bound on order of log square n over epsilon. And for any approximation, there's lower bound of log n over log n also, which we did not talk about. Okay, so this lower bound is based on prior work, but it has to use some correlation in the distribution. We can talk about it later if someone wants to. And what are some open questions left? The obvious question is to reduce this gap. Can you get it to something tight? And even for exact shortest path, we don't know complete answers. Yes, I will leave you with this. This paper of Guruswamy Onag gives you a lower bound of omega of log n over log n for finding exact shortest paths. And this paper of Chong et al. Gives you an order of square root n in the number of passes for finding exact shortest paths. This is a large gap, and we don't know how to close this. And that's it. Yes.
Better upper bound, I mean, again, this is not for pass complexity, let's say we're only thinking of single pass.
Mm-hmm.
Is there anything better known when it's like, random order or something, or it's doesn't randomness doesn't count for this problem?
I don't know now for random order. I haven't checked. I think it does. Actually, no, it does. So I think you'll be able to, let me see. Let me try to remember. You can grow BFS trees up to some value. You can find connected components and a lot. You can do a lot of things with random order. They do help. I don't think I can give you exact bounds now.
Because the low ones are like random graph. And then at the end, I count S to one and vertex and T to all of it.
Okay.
And you have to find whether there was an edge between UV or not. Because in a random graph, either there is an edge or the darn is talking water.
Oh.
Okay.
Wait, you're still talking about passes, right, when you say?
No.
Yes, single pass. So the string is a solid random graph for the first part.
Right.
And the second part will just give you two edges.
Okay,
Connecting S to U and T to V.
okay,
If UV was an edge in the random graph, your distance is 1.
yes,
If there was not an edge, your distance with high probability is around volume.
no,
So you cannot distinguish between these. But in a random graph, in a random order string, it's still like 1 for probability, those two edges S and T appear at the end. And you see half of the random graph is not going to. There are these versions of random order explaining your random stuff. I pick a random graph, I partition it into 2 parts. Still, the first part is half of a random graph, so you have to compress. And there is a 1 for probability that the edges incident on S and T appear on the second part. So the probability there's a 1/8, the edge UV is in the first part, and SU and TV are in the second part. In that case, you have to solve the same problem.
oh, yes.
So I was going to say it helps if you want to find other things like connected components, you can do it in much less space. A number of connected components and those things. And for shortest path, these kinds of specific distance problems, no, like he said.
And for single pass, let's say I want to find the exact shortest path, is it omega n square, or what's the bound for exact shortest path in single pass space?
Yes, because this at least is not hard to see in these kinds of examples. If you just have like a bipartite graph where each edge appears with probability half, and then you can just choose 2 things later and you have to figure out whether this edge exists or not. It's like some kind of index type bounds and you can get omega of n square.
So that's fine, John. Questions?
We say in one sentence about the de-randomization. What do you do there?
The what?
The de-randomization.
Oh, so the main thing was to figure out these QE values, and instead of sampling them, how do you store this? You can do something where you actually just stores. Let me say it like this. There is this framework called a merge and reduce thing where you're able to store sparsifiers for these QE values instead. So you're able to directly store this tree and figure it out without actually storing the QE values explicitly or taking them. Okay. So no, let me see if I can say something in a couple of things.
You're still sampling.
Yes, so that's why I started with the merge and reduce thing. Okay. So you can think of it as a cut sparsifier. Okay, so that you can de-randomize it, and this algorithm you can imagine it as a kind of a cut sparsifier also. But it is a sparsifier for these QE values instead.
You mean like a weighted?
Yes, it is going to be weighted. The final edges that you store will have weights, but it won't be the initial QE values they started out with. It is something that will represent the QE values. Okay, like a weighted graph which represents the QE values without actually storing them. That is something you can get.
So if you just pick QEs and put them on your graph, and then you compute the call sparsifier of that.
And then you do deterministic thing.
So yeah, the call sparsifier lets you know deterministic you can do it.
Sure.
So now you have call sparsifier of the graph, you compute the shortest path on the path. Like, the college classifier does the task of sampling.
Yeah, exactly, so that's where it comes.
See, that's it, you don't need, like, in an unweighted version, you literally just put Q on every edge and compute college classifier.
I think it is still unclear how you would actually say that these things are like, it's not the main thing you would want is the bad tree property to be just represented here, no? So I don't think just the cut specifier would be enough. You'd have to, you need a different kind of specifier which is similar, but the main thing you would want to capture is if you have a lot of bad edges for a particular tree, for that same tree, you would need the same thing of a lot of bad edges to be captured here as well. And for this, I think you need to do something slightly different.
This was like a variant of like de-randomizing cut specifier.
Yes, exactly.
Randomize this kind of bad tree controlling specifier.
Yes.
Oh. Is it very hard?
Sorry?
Is it very hard?
No, I don't think so. Once you know that cut specifiers can be done, you can adapt it almost directly to this with just minimal tweaks and changes. I don't think it's very hard. No, it was kind of straightforward, but there's some literature about cut specifiers. If you know that, then it's not hard. Otherwise, then I think it's hard. Yes.
So, how does this work in the sense of like, instead of bad trees occur with low probability kind of statement that you had before here, some of the specifier avoids all possible bad trees, or?
It's going to, so let me say, instead of this, like the analog of F is going to be a set of edges with weights, so that for a bad tree, it had a lot of bad weight edges. So for that same tree, if you compare and find shortest paths here, these edge weights are going to be at least as much as what that tree had. Okay, so it is not going to, like, kind of, yes, you can say that the bad tree is not going to end up as your tree. It just directly almost avoids them, that much I can say, yes. If your weights ended up being very bad, then maybe you will get it, but that's not going to happen. Yes.
A bit of a vague question, but could you help me motivate, like going from one pass to multi-pass? Like what is it for?
I think in one pass for this one at least, we know like right answers for like every range, like a little omega of n, we know this. And for one pass, at least for shortest path, you can do these kinds of tricks that they are saying. You can just maybe make them focus on any pair and find the shortest path by just giving S and T edges at the end. This is something that at least you can't do in multiple passes. If you know these ST edges, you can focus based on them and figure something out, do this kind of iterative optimization thing. Well, I guess it's natural to ask if you just see the graph multiple times, can you help or not? This is one thing, but at least for shortest path, I think it has more motivations because these kinds of tricks where you make them focus on any particular pair of vertices don't work in multipass. So yeah, we know complete answers. We don't know what is going to happen beyond this. We have to start.